Hello. In this video, we are going to look at finding surface area. Our goal is to go through and find the area for part of a surface. So let's start off by drawing a picture. We have a surface. I'm going to draw a region beneath the surface. I'm going to draw a rectangular region, but this could also be a general region or a polar region. And what this patch beneath the region is going to do is it's going to define the part of the surface that we want to go through and find. Okay, now clearly it's not on the surface, but the idea is that you extend it upward and it just hits the surface, and where it hits the surface is going to be the part of the surface that we want to go through and find the area of. Okay, so let's go ahead and draw that so you can see it more clearly, right? So you're going to extend this upward, it's going to hit the surface. Extend this upward, hits the surface. Same over here and over here. And then if we just go through and draw the part of the surface that would be directly above this line, the part of the surface that would be directly above that line, part above that one, and so on, what we get is we get this little patch. So our goal is to find the area of that patch. Okay. Now, the way in which we're going to go through and do that is going to be similar to what we've done from the last few sections, where we're just going to chop it up into pieces. Okay, so it's the same thing we did, except we were finding volumes in previous sections, but in this section we're finding surface area. So how do we do that? So what we're going to do is we're going to go ahead and draw a little mini rectangle in our bigger rectangular box here. And you're going to go through and you're going to extend that upward until it hits the surface, and it's going to create a little patch on the surface, and we're going to find the area for that little patch. And then what you can do is you can just mimic this and move it around the rest of the rectangle, finding the others, right? So you could just draw another little box next to that, and then find the little patch next to that patch, and so on. So you could go through and do a strip. You know, we've talked about the strips in the previous sections. So we could find a little strip of patches, right? And so by going through and covering this entire rectangular box with these little pieces, and then finding the areas directly above each one, we could go through and add up the area on the entire patch. Okay, so to do that, what we need to do is we need to figure out how do we find the area for one of these little patches. So to go ahead and figure that out, so let's zoom in and draw a much bigger picture. Okay. All right, so this is the little box, the little rectangular box that's directly beneath the surface. And then we're going to say, all right, so from there, we're going to go up, hit the surface, go up, hit the surface, and so on. And then, so now what we want to do is we want to draw the surface that's going through those points. So the idea is that this is not going to be a smooth edge. It's going to be a curve. So it could look something like that. Could look something like that. Like that. Like that. All right. And so our goal is to go through and find an approximation. So it doesn't have to be perfect. We just want to find an approximation for the area for this piece here. Okay, this patch of the surface, this portion of the surface. All right, so how could we go through and do that? Well, what we're going to rely upon is a technique that we learned in a previous video, and that is we could go through and we could find the area for a parallelogram given if we have two of the sides by using the cross product. All right, so this is going to seem to come out of nowhere. But if you recall from a previous video, we said that if you have, hold on, that was supposed to be a vector, not a line. All right, so let's try that again. All right, so suppose we've got a vector and another vector. Then, so this is vector A, this is vector B. If you go through and take those and extend them, then the area of this patch is given by the length of A cross B. All right, so that's the area for that parallelogram. So how does this apply to this situation? Well, if we can go through and define a vector that points from one side over to the other, covers this side, this piece here, and we could define a vector that points from here to here, then we could go through and find the length of the cross product of those two vectors, and it would give us an approximation. That's important to talk about. This is an approximation. It's just like in the previous sections when we're going through and finding volumes, or if you want to go back all the way to Calc 1 and you're finding area under the curve. It's okay if it's off by a little bit, because the idea is we're going to take this box, right, that's directly beneath it, and we're going to shrink it. And as we shrink it, our approximation will get better and better. Okay, so our goal is to find, essentially, our next goal is to go through and get an approximation to this vector. Oh, hold on. So what we want to do is we want to find something that points kind of like this and kind of like this. Right? And if we had those two vectors, then their cross product would get us the area roughly, an approximation for so the area for that piece there. Okay, so how could we go through and do that? That's our next goal, is to figure that out. All right. Well, so let's think about that. So what we want to do is we want to find, this red vector, this guy right here. And so what we have is the only thing that we have. Oh, and I should have mentioned this corner here. We're going to go ahead and say that's f of x. We're going to say that's x sub I, y sub j. And don't forget, I haven't mentioned it. We do know the surface. The surface is f of x, y. All right. So that's giving you some time to think about it. Well, if we were at this point here and we drew a tangent line on the surface in the x direction, it would look something like this, like the red line here. That might not be perfect, but that's okay, because we don't need this red line exactly. We just need an approximation to it. So if you were to go through and draw a tangent line there, let's just use one more color here. It's going to be in blue. It would look maybe like this. It's pretty close, right? It's about like that at that point. It's about like that, right? So it's pretty close. And so, that would be, if we drew a tangent line, that's what it would look like at that point. So it's pretty close to our red vector. Close enough that what we're going to do is we're just going to go ahead and say that they're good enough. And if we could go through and take that tangent line, if we could take the tangent line information, we could use it to define what this red vector is. All right, so what do we know? What information do we have about that tangent line? Well, so that tangent line is the tangent line that's directly above a step in the x direction, right? This is directly in the x direction. If you go through and were to look kind of over here at our picture, so this is the x direction. Notice how I've drawn the sides of the box here. They're parallel to the x direction, so this is in the x direction, right? So, well, if you go back to the last chapter, the last chapter on partial derivatives, one of the things that we had was the partial with respect to x is the slope of the tangent line in the x direction, right? It's the amount of change that you'd get if you took a step in the x direction. So we know the slope for this line is the partial with respect to x. Okay, so not only that, we know something else too, right? So in the last chapter, we also said in the section where we covered tangent planes, we had to go through and take a slope and turn it into a vector. So we know that we can go through and take the partial with respect to x, and we can represent that as a vector using 1, 0, partial with respect to x. So that's explained in more depth in that tangent plane section, but we know we can take this slope and we can represent it as a vector. So slope as a vector. Right, is this guy. And so once we've done that, the next thing that we could do, so that's not going to be the red vector here, right? So what this says, if you want to interpret it, it says if we took a 1 unit step in the x direction, we would get partial with respect to x vertical change in height. That's what this says, right? Because this is the change in x, change in y, change in z. So right now, this vector is defined for a 1 unit step in the x direction. Well, how big of a step do we have in the x direction? It's going to be this length of a step. So what is this length? Well, it's the side of the box that I drew that's directly beneath our object. And you'll notice in previous videos, we've gone through and we've labeled that change in x. So what we need to do to take the slope for this blue line and turn it into this red vector is to take that slope and multiply it by change in x. So instead of a 1 unit sized step, we're going to have a change in x sized step. So if you just take change in x, multiply it by 1, 0, partial with respect to x, you'll get change in x, 0, partial with respect to x, change in x. And that's going to be our red vector, right? So let's call our red vector, or an approximation to our red vector, I should say. Right, so the blue line may not fit exactly right on top of the red line, but that's okay. All this stuff, as we take these boxes and make them smaller, the blue line will fit onto the red vector better and better, which will fit onto the patch of the surface better and better. And so as we take the limit as these number of little boxes goes to infinity, we will get better and better approximations until it fits perfectly right on the surface. Okay, so the idea is next to go through and do the exact same thing. So we could, in the y direction. So if I were to go through and draw a tangent line in the y direction, right at that point, it would look something, maybe about like that. So it doesn't have to fit right on top of the red vector. That's okay. It's just, we're just approximating it. And so same thing, we could go through and find the slope for that. Right, so we know this is now a step in the y direction. This is the curve is in the y direction, and so we could find the partial with respect to y is going to be the slope of that tangent line that's in the y direction. Okay, and then from there we could go through and turn that into a vector. So that's going to be 0, 1 partial with respect to y. So that's saying if we take a 1 unit step in the y direction, we would get partial with respect to y, vertical change in height. We could then go through and take that. All right, so let's go ahead and kind of connect this. So the slope as a vector. And then we could take that and we could turn it into, we need a change in y sized step. This is for a 1 unit step. So you need to take change in y and multiply it by that. And then we'll get 0, change in y, partial with respect to y, change in y. All right, and so now what we've done is we've gone through and we've defined these two vectors. If we take the length of their cross product, it will get us the area for this little patch of surface. So we'll do I, J, K. And then we'll have 1, 0, oop, not 1. Hold on, I forgot we multiplied by change in x. Change in x, partial with respect to x, change in x, 0, change in y, partial with respect to y, change in y. So we get I, and we get 0 times partial with respect to x, change in y. So we're going to have negative partial with respect to x, change in x, change in y, then minus j, and then we'll have partial x, or change in x, partial y, change in y. So we could rewrite that as partial y, change in x, then plus k, and we'll get change in x, change in y times 0, or minus 0. All right, so that's going to be our cross product. And then we want to take the length of that. So the length of that is going to be, hold on, let's do this. I want to find the, actually, let's just kind of clean this up a little bit. All right, so we've got V, we'll call this one W. So this is V cross W. And then the length of V cross W is going to equal the square root of the component squared. So we want to square this one. So we get partial with respect to x squared, change in x squared, change in y squared, plus partial with respect to y squared, change in x squared, change in y squared, plus change in x squared, change in y squared. And then we can go through, and so that's going to be the area for our patch, our approximation to the area for our patch. So now we've got, there's our patch, and we have an approximation to it. So we could simplify that. We could factor out the, we could pull out the change in x, change in y. And this becomes, I'm going to label some other stuff too. So this is, notice what we said is we said we were using this corner, this point where we have x sub I, y sub j for all of our calculations. So the partial with respect to x is at x sub I, y sub j. The partial with respect to y is at x sub I, y sub j. Plus 1. So if we factored out this, then we'd only have a 1 left there. And then we'd have change in x, change in y. And so that's what we get for a single patch, right? So now that we've got the area for just this single patch, that's directly, above a, IJ located little rectangle, what we want to do is now we want to vary that across the whole object. And the way that we could do that is the same technique that we used in the previous sections, which is just to throw a limit as m and n go to infinity, and a double summation. It doesn't matter the order here. I equals 1 to n, j equals 1 to m, and then we have square root this thing, partial with respect to x squared. Let's do a little better job than that. Let's go ahead and actually put the point in here. Xi, yj, partial with respect to y squared, xi, yj, plus 1, change x, change y. And the order there does not matter. It could be change x, change y, change x. Sometimes you'll see with proofs, you'll see someone put change a. That's fine. All right, and so now if you look at this, this is exactly the format that we had for a double integral. So if you go through and substitute this, you go through and rewrite it, do limit mn to infinity, sum I equals 1 to n, sum j equals 1 to m. This is, it doesn't really matter. We'll use g. This is g of x sub I, y sub j. Change x, change y. You go back and watch the previous video where we defined what a double integral is. This is the format for a double integral. So we can jump right to the double integral here and say that this is the double integral of g of x, y, dx, dy, over, in this case, from a to b and from c to d. Okay, so all of that was the derivation. Oh, hold on. So I forgot to change back here. You do need to change back to this format. So this would be the square root partial with respect to x squared plus partial with respect to y squared plus 1 dx dy. And that right there is our definition for surface area. So all of that was, as I was starting to say, all of that was specific to this situation. I've got a rectangle that's directly beneath the object, beneath the surface of the object that we want to find, and it's got sides A and B and C and D. All of it was specific to that instance. However, I could go through, redo this derivation. Instead of doing a rectangular box beneath, I could do a general region. I could do a polar region. If I did a general region or a polar region, then all throughout here, we would have some slightly different things. You might have, R, change in theta, so you could have all those things would shift, but the general steps here would all be exactly the same. And so what we can do here is we can just kind of generalize this result and say that the surface area formula is going to be over a region, we're just going to call region R, and it's partial x squared, partial y squared, plus 1, and we're going to put dA to leave it unspecified. So this way you could go through and you could do it over a general region, you could do it over a polar region, however you want. And of course, this is for the idea is that we're finding surface area for a surface f of x comma y, and then R is the region that's directly below. Okay, so that is the derivation. That's where the formula comes from. So when you're looking at surface area and you're like, wait, why does it have partial x squared, partial y squared plus 1? Where does that come from? What does that have to do with surface area? Well, that's the point of what we just did, is to go through and explain where that comes from. Okay. It comes from the fact that we're using we're finding this vector and it's partial with the partial of f with respect to x, and we're finding this vector and its partial of f with respect to y has those in the components. Anyway, all that's kind of neat. But let's go through and do some examples. So using the surface area formula is not especially difficult. Let's say we want to go through and find the area for the part of the surface so part of the plane, x plus 2y plus 6z equals 6. That is in the first octet. Okay, so if we look at our surface area formula, notice how our surface area formula has z by itself. We have z equals f of xy. So we first need to go through and get a z equals for this. So to do that, you need to solve for z. So we could do 6z equals negative x minus 2y plus 6, and then z equals negative 1/6 x minus 1/3 y plus 1. Okay, so that gives us our surface. Now we need to figure out what is the what's the region that's directly below the part of the surface that we're trying to find. So the thing that can be helpful for that is it can be helpful to go through and sketch it. Now that may not always be necessary depending upon the information that they've given you. In this case, they just have told you it's the part of the plane that's in the first octant. It really is not enough information given for us to go through and figure out what that region that's directly beneath our surface is going to be without doing a sketch or doing something. So I would go through and sketch the object. In a previous video, I discussed how some people don't like to sketch the object. So I will show you a way to do it without sketching the object, but I don't think the object is especially difficult to sketch. So I recommend at least trying it. All right, so how could we go through and sketch this? Well, the easiest way to do it is if you go through and you set x to 0 and y to 0, that will get you the z-axis, okay? And so you could go through and find the z-intercept by setting x and y to 0. So if x is 0 and y is 0, then you just get 6z equals 6. And so we'd get a z-intercept of 1. Right? If you go through and set x equal to 0 and z equal to 0, then you're going to get 2y equals 6. And so we'll get a y-intercept of 3. And then if you set y and z to 0, you get an x-intercept of 6. And we're able to go through, and that's all there is to it. That sketching the object is that easy. All right, so that's the piece of the plane that's in the first octant. So what is directly beneath our surface? It's going to be this stuff here. That's the part that's directly beneath. If you were to look straight down the z-axis, the only thing that you'd see is just that region. And so let's go through and try and sketch that. What do we know about it? We know that if we look straight down, you just see the x and the y-axis. So we know we're going to have an x-intercept of 6 and a y-intercept of 3. We're going to have the line like that. All right, and so what we need to do is this is going to be our region that's directly beneath. That's going to be our R. And so we need to figure out how to add across that region. Okay, so that's not a rectangle, right? So we can't go through and use our rectangular method. That's a general region. So your next thought is it type 1 or is it type 2? It's both, right? So we could use type 1 or type 2. Typically what I tell students is that if you have a choice, then type 1 is usually a little bit easier. So type 1 goes from the bottom of the object to the top of the object. So if we're going to set this up, so let's do this in 2 steps, right? So I've kind of skipped some steps here. Well, we haven't skipped anything yet, but let's go through and do this in at least a little bit more organized fashion. So once you've gone through and you found your surface, what do you need? You need the partial with respect to x and the partial with respect to y. So we haven't done that yet. So let's go ahead and do that. This is f of xy. So the partial with respect to x would be, if you differentiate this with respect to x, you're going to get negative 1/6. The partial with respect to y, you're going to get negative 1/3. And then what we want to do is we want to take the square root of those squared and add 1. Now I'm going to jump all the way over to here. So now we're going to have our double integral, square root. We're going to take partial with respect to x and square it, that's 1/36. Take the partial with respect to y and square it, that's 1/9 plus 1. So this is the partial with respect to x squared, partial with respect to y squared, plus 1. And then what I'm going to do, and this is the way that I recommend you do it. At this point, don't set up the bounds yet. What we're going to do is we're just going to put dA and then r. So what I recommend when you go through and do these problems is first go through, find z, find partials, get to here, and then you could simplify this, but then stop. Then go through and do the region stuff. So that's kind of what I was saying, but I'm kind of skipping some steps here. Is that we didn't do this yet. All right, so if you add this up, this is going to be 4/36 and 36/36. So 36 and 4 and 1, we're going to get 41/36. dA. All right. So once we've got to here, then you want to go through and do all this stuff because we have to figure out what r is. So you draw your pictures, and then so now it's really, is it type 1 or type 2? And as we just decided, it's type 1 or type 2. It doesn't really matter. But what I recommend is that if you have a choice, it's easier to do type 1 than type 2. Usually just format-wise, people just get more comfortable with that. So type 1 goes from the bottom of the object to the top of the object. So we've got to find a way to define. Let me go ahead and write this. It's getting a little small, but with type 1, you do y to y and then x to x. All right, so you go bottom to top. That's what you do first. So we can over here we can just throw a dy and a dx. That's the order. All right, so once we've chosen type 1, what you want to do is just go ahead and throw y equals x equals x equals and dy dx. So the bottom of the object, defining using y equals, well, this piece here, that's part of the x-axis. The x-axis is at y equals 0. How could we find the equation for this line? Well, we could use our old favorite y equals mx plus b, right? So we know that the y-intercept for this is 3. And then the question is, what's the slope? Well, we went down 3 over 6. So that's in the ratio of 1 to 2. So that's negative 1/2 x. So we have negative 1/2 x plus 3. And then for x, we can go through and we want to go from the left side, which is at x equals 0, and the right side is at x equals 6. And then this stays, let's simplify it to root 41 over 6. Okay, so let's recap that because I did kind of go out of order. You want to first find the surface, get the partials, square the partials, add 1, and then just stop. I mean, you could do one step of simplifying, but then stop. Then go through and we're like, all right, well, what is the object? What part of this? Because this would work. This stuff that we've done will work for any part of our surface, negative 1/6x minus 1/3 y plus 1, any part. The question is, well, what part? So once you've gotten to here, we're like, all right, well, what part? So you can then graph the object, sketch the base, right? So by looking straight down the z-axis, we would just see this piece. And then we could go through and set up the bounds. All right, so to go through and evaluate the integral, let's just go to the next page here so that we're not all scrunched. So we have 0 to 6, 0 to 6, 0 to negative 1/2 x plus 3. and then root 41 over 6. dy dx. So from there, it's pretty much plug and chug. So we do 0 to 6, the antiderivative of well, let's just move the 41 out over 6 out front. The antiderivative is just going to be y, 0 to negative 1/2 x plus 3 dx. And we get root 41 over 6, 0 to 6, plug in, get negative 1/2 x plus 3 dx, and then we can integrate. And so we're going to have what? This is x squared over 2, so we'll get negative x squared over 4 plus 3x, 0 to 6, root 41 over 6. Plug in 6, we get negative 36 over 4. That's negative 9. Plug in 18. Negative 9 plus 18 is 9. So we get 9 root 41 over 6 equals 3/2 root 41. And that would be the area for the part of our surface. Okay, so I mentioned that you could go through and try and find the region that you're integrating across, find the R, without having to go through and sketch the object. How do you do that? Okay, well, what you can do, right, so since we're finding the area for the part of the surface that's in the first octant, the first octant is everything that's above the x-axis, everything that's above the xy plane. And so what is the xy plane? The xy plane is defined by z equals 0. So what you can do is you could take this equation, x plus 2y plus 6z equals 6. And you could go through and set z equal to 0. If you do that, you'll get x plus 2y equals 6, and then 2y equals negative x plus 6, and then y equals negative 1/2 x plus 3. Look at that. All right, so this equation came from where the surface hit the xy plane. So this line right here is the part of the plane where z equals 0. Okay, and so if you're trying to go through and avoid sketching the surface and you're just trying to sketch the base, then what you need to do is you need to identify where your surface hits the xy plane by setting z equal to 0. And then if you've got that, right, once you've got this piece, if you go through and just, draw a coordinate axis, you say, all right, well, I've got, the line 3, and intercept of 3, and negative 1/2 slope 6. Then from there, you can go through and say, all right, well, what else do I need? Well, if it's in the first octant, it means where x and y and z are all positive. Well, this is the line where x equals 0. And so that's going to give us, this side is where x is positive, this side is where x is negative. This is the line where y is 0. This side is positive, this side is negative. And so we've got our left and our right side, left and our bottom of our object to go with the top of the object that came from setting z to 0. So this is, you can go through and do this. Personally, I think this makes the problem harder, but that's my take on it. So I think it actually makes it easier to go through and sketch the object, and then from the sketch of the object, then transition, to this, to the region that you'd see if you looked straight down the z-axis. But I think maybe the issue there is that this is what I practice doing, and so that's why it's more comfortable for me. If you practice doing this all the time, figuring out, well, what do I need to set equal to 0, or what do I need to go through and plug in so that I can get to immediately just 2 variables, then maybe you get good at it. It becomes easier to do it that way. All right, let's go through and do another example. So we've got find the area of the part of the surface f of xy equals z minus z equals 4 minus x squared minus y squared. That is above the plane z equals 2. Okay, so in this case, we've got our surface. We can immediately go through and do partial with respect to x, negative 2x, partial with respect to y, negative 2y. We could do the square root of the partial squared. So we're going to get negative 2x squared would be 4x squared. Negative 2y squared would be 4y squared plus 1 dA r. So that's what I recommend you do first, which I had kind of skipped over part of that in the previous example, when I immediately went to the graphing of the region. So that's the order I would recommend that you do, is you go ahead and do that first. Now the region. All right, so because this formula is going to enable us to find surface area for any part of this surface. Now the question is what part? All right, so again, this is where you get into, do you want to sketch the entire object, or do you want to just try and sketch, figure out what the base would be without doing that? If the object is easy to sketch, I like to sketch it. And so this is just a paraboloid. It's a fairly simple object. It's got a z-intercept. If you set x and y to 0, you'll get z is 4. So it's got a z-intercept of 4. And then it's opening downward. So it looks like a parabola, right? So if you just covered up the y part here, right, and made this if you just ignored the y part, you would just have a parabola. But it's a parabola with two pieces. So that's a paraboloid. Right, so if it opens downward, right, we're going to get an intercept at 2 and at negative 2. How did I figure that out? If you set y to 0, we'll get the cross section, right? So this is a quadric surface. You'll get the cross section if you cover up y equals 0, and then that the intercept there will be when you set z equal to 0, you'll get the intercept. I'm butchering this. All right, so this is what I'm doing. I'm just doing it in my head. All right, so you've got this. Okay, if we want the cross section that's on the xz plane, I'm setting y equal to 0. So I'm getting here. I have this. So that's going to be this surface here. And then to figure out what the x-intercept is, I'm setting z equal to 0 and getting x equals plus or minus 2. Okay, so all of that. That's just doing all that, but we're just doing it in our head. All right, so we get this. All right, and now you can go through and repeat that, but set x to 0 and then z to 0, and you'll get y equals plus or minus 2. All right, so that's our surface, z equals 4, then minus x squared y. 4 minus x squared minus y squared. All right. If that's all they'd given us, right, then we actually wouldn't have a region. So we need something below that, because that actually extends forever. The surface extends forever downward. So it's telling us is that the bottom of the object is going to come from the plane z equals 2. So if you just take, here's 0 to 4, so just stop right in the middle there, put a 2. And then if you draw a plane, right there at z equals 2, so the plane's going to look something like this. Right, the idea is that plane is going to hit the paraboloid, where does it hit? Well, you could just move over from the side of your plane. It's going to hit here, 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 and the back side, I guess it didn't really move far enough back, but it's going to hit there. And so you get this circle where your plane z equals 2 chops through the object. All right. So where is that? So what we need to know is we need to know where that circle is. And to figure that out, what we can do is we can go ahead and take z equals 4 minus x squared minus y squared, and z equals 2, right? So this circle that I drew, it's clearly smaller than where we're intersecting the xy plane, right? So we're hitting the xy plane here and here and here, right? So you got a bigger, that's a bigger circle, so it's clearly smaller than that. The question is, how big is it? To figure that out, what you can do is you can go through and set these two equal. So you get 4 minus x squared minus y squared, and then z equals 2. And from that, we can figure out that x squared plus y squared equals 2. And so we have a circle of radius 2. Square root 2, sorry. Circle of radius square root 2. Okay, so that's the region over which we want to go through and do our integration. That's going to be R, is we want to integrate inside of that. Okay. Now that's if you go back to our previous slides here. So we said it's directly above the rectangular region on the XY plane. This one, it's directly above this triangle that's on the XY plane. So you'll notice this is not on the XY plane, but you could think of just kind of extending it downward, right? If the way to think about these are the R regions is it's what you'd see if you just looked straight down the z-axis. That's what you're going to integrate over, is the thing that you'd see if you looked straight down the z-axis. And so if you took this red line and it just extended it, the red circle, and extended it downward onto the xy plane, you'd get a circle, okay, that is x squared plus y squared equals 2 on the xy plane. So I just want to make sure that's clear. So yes, the red line, the red circle, the way that I've drawn it here, it's not sitting on the xy plane, but you could just shift it downward so that it landed on the xy plane, and that's going to be our region of integration. That's the way these work, is that you take the region that you're integrating across. It is just in two variables, so it's on the xy plane. But it might be, in terms of a picture, it might look like it's above it, but we just extend it downward. And so to go through, and if you wanted to sketch this in 2 dimensions, if you wanted to sketch what you'd see if you looked straight downward, you can do that. So it's just going to be the circle that has radius root 2. So that's what you'd see if you looked straight downward. That's our R. Okay, so how do you proceed from there? Once we've got the circle, we want to go through and set up the integration. So since the region is a circle, what we want to use is polar coordinates. So the way that we set that up, so with polar coordinates, you go from R inner radius to outer radius, and then the theta values. We want to convert this into polar coordinates. Since we have x squared plus y squared is in the problem, you can use x squared plus y squared equals r squared to convert this into 4r squared plus 1. The dA becomes r dr d theta. And then what would our bounds be? So we want to go from the inner radius to the outer radius. So the inner radius is at the center, so that's going to be 0. The outer radius is going to be the radius for our object, which is root 2. And then since it covers the whole circle, we go from 0 to 2 pi for theta. All right, so let's go to the next page and evaluate this. So we've got 0 to 2 pi. We have 0 to root 2, square root 4r squared plus 1 r dr d theta. This is just a u substitution, so we have u equals 4r squared plus 1, du equals 8r dr. To get the 8, we could just add that in, offset it with a 1/8. We get 1/8, 0 to 2 pi. The bound changes, plug in 0, you'll get 1. Plug in root 2, you get 9. This becomes root u du d theta. Then we can integrate. This is u to the 1/2. The antiderivative u to the 1/2 is going to be 2/3. U to the 3/2. 1 and 9. 2/3 times 1/8 is 1/12. 0 to 2 pi. Plug in 9. Take the square root, you get 3. Then cube, you get 27. Plug in 1. Square root, you get 1. Cube, you get 1. That's 26. We could move that out. 26 over 12 would be 13 over 6. 0 to 2 pi. D theta. That just turns into 2 pi. And this turns into 13 pi over 3. So there's a second example. And then in my notes here, I did one more. Find the area of the surface. Find the area of the part of the surface two y plus 4z minus x squared equals 5. All right, so there's our surface. And then we're also told that lies above the triangle with vertices 0, 0, 2, 0, and 2, 4. All right, so the first thing that you should do, go through and solve for z to get your f of xy. So f of xy equals z equals, all right, so to get that, we're going to swing these two over to the other side. So we'll have 5 minus 2y plus x squared. That would be, so 4z is going to equal 5 minus 2y plus x squared, and then we need to divide by 4. So you get z equals 5/4 minus 1/2 y plus x squared over 4. And then, so that's our f of xy. And then the partial with respect to x, derivative of 5/4 with respect to x is 0, 0. So we're going to get 1/2 x. Partial with respect to y, negative 1/2. And then we can take those and create our formula. So we're going to have double integral square root 1/4 x squared plus 1/4 plus 1 dA over R. So that's the order that I would recommend. Go ahead. First, focus on getting your surface defined, then finding the partials, then creating the formula, and then second is to go through and look at the region. All right, so the region that we're integrating across is we're told it's the triangle with vertices 0, 0, 2, 0, 2, 4. Okay, so you're going to notice that I'm going to do something different in this problem. The previous two problems, I sketched the surface. Why am I not going to sketch the surface in this one? Well, it's because they specifically described the region that my surface is above, right? In this problem, they say to find the area of this part of the surface that's above this, that's below the, find the area of this that's above this. We can't tell what our object that we're integrating across is. We can't tell what this red circle is just by going through and looking at these two pieces of information. We need to go through and get some idea of what the object looks like, where the intersection is between these two. You need to figure out what the R is. The R is not explicitly described. Here, is the R explicitly described? No, it's find the area for the part of the plane that's in the first octant. So that's why you need to sketch the surface, is to figure out what the R is. Okay, to figure out what the region is that you're integrating across. Now look at this one. Find the area, the part of the surface that lies above the triangle. It's being explicit. It's telling you what the region is, right? So you don't need to know anything about the surface to go through and figure out what R is, because it's so explicit. So if the surface is explicitly described, then you don't need to go through and do any sketching of the surface. So I wanted to show you that, because just to show you that I don't always sketch the surface if I don't need to. Okay, so how do we go through and turn these three vertices into our R? Well, you want to go ahead and draw a picture. We have 0, 0, 2, 0, 2, 4. All right, so we get this picture. We know this point here is 2, 0, and this point is 2, 4. We need to turn these into equations. So this bottom piece here, that's y equals 0. The right side here, that's x equals 2. And the top here, right, so that's a line going through the origin. So we know we know how to create lines using mx plus b. So we have y equals, and we know that y-intercept is going to be 0. Now what's the slope? So we went up 4 over 2. So that's a ratio of 2 to 1. So it's going to be y equals 2x. All right. So that gets you to here. And now we need to figure out type 1 or type 2 to go through and set up the integral. So it could be either one. We could use type 1 or we could use type 2. So we have a choice. If you have a choice, what you could do, which you should do, is you should look to your integral, which order of integration would be easier on this problem. Would you want to integrate with respect to x with it looking like this? I would not. I would prefer to integrate with respect to y, because x is treated as a constant. This whole thing is just a big constant. So that suggests we should do type 1, where you have y equals to y equals, x equals to x equals. And then this becomes square root 1/4 x squared. 1/4 and 1 is 5/4. And we get dy dx. So y equals, what's the y equals going to be? So that when you're doing y equals, it goes bottom to top. So the bottom is that y equals 0. The top is that y equals 2x. Then you go left to right, which is 0 as the left side, x equals 0, and the right side is x equals 2. And we get to here. And now we can go through and evaluate this. Integrating with respect to y, you treat x as a constant. So we're going to get 0 to 2. Let's just copy the whole thing first. All right, so we're going to have 0 to 2x square root 1/4 x squared plus 5/4 dy dx. So the antiderivative of that with respect to y is just going to be that times y. Zero to 2x, 0 to 2, plug in 2x, we get 2x, 1/4 x squared plus 5/4. Plug in 0, you get 0. And so that becomes our integral that we need to evaluate. I'm going to take that 2 and I'm going to move it out front, actually. This is a u substitution. We get u equals 1/4 x squared plus 5/4. Du is 1/2 x dx. So we need a 1/2. And we could offset that with another 2. So we're going to get 4 integrals. And then plug in 0. You get 5/4. Plug in 2. 2 squared is 4. 4 times 1/4 is 1. 1 plus 5/4 is 9/4. Then we have root u du. This is u to the 1/2. The antiderivative of that is 2/3. U to the 3/2. 5/4. 9/4. And we get 8/3. Plug in 9/4. 9/4 to the 3/2. You're going to square root first. That's going to be 3/2 and then cube. So we're going to get 27/8 minus, and then plug in 5/4. You square root first, which is going to give you root 5 over 2, and then cube. And so we're going to get 5 root 5 over 8. The 8's here cancel with the 8 there, and so we're going to get 27 over 3, which is 9, minus 5 root 5 over 3. Okay, so that concludes the surface area video. Thank you for watching. I'll see you next time.